Good morning. So today we're going to leave classical field theory mostly behind and move on to quantum field theory. And the subject of today's class will be canonical quantization of the Klein-Gordon field, which is a free, real scalar field. So this is the simplest possible example of the quantum field theory. And the way we're going to proceed is through canonical quantization, which will work very much in the same way as you're used to from ordinary non-relativistic quantum mechanics. So in quantum mechanics, the usual procedure is to take our position and conjugate momenta and promote them to operators and impose commutation relations among them. So if we have some set of generalized position, QA, and the conjugate momentum, PB, the usual thing is to impose this kind of commutation relation. Remember, we're always in this course going to set h bar equal to 1. So they're just a single position and a single momentum. This would just say that the commutation relation is I h bar, but h bar is equal to 1. If we have multiple, we impose this kind of commutation relation where the momentum associated with a different generalized coordinate commutes, and all of the positions or generalized coordinates commute among themselves as do the momentum. Okay, so one thing to note in quantum mechanics is that we treat time and position very differently. So time is just a parameter. Position is an operator. What we want to do is move to a special relativistic version of quantum mechanics, in which case we want to treat time and space in the same way. So you can imagine there's two possible ways to do that. Either we could promote time to an operator, or we could demote position to a parameter. And both routes are possible. Promoting time to an operator turns out to be much more complicated in practice. For those of you who take the string theory course later in the year, you'll see string theory is developed along those lines, essentially promoting time to an operator. We're going to take the opposite approach because it's simpler, and we're going to demote position to a label. And so in that case, the analogy we used yesterday to understand the relationship between particle mechanics and classical field theory basically carries over to what the commutation relations we need to apply to quantize the Klein-Gordon field. And so in the Schrodinger picture, the natural generalization of these commutation relations is we should impose that the field operator now the commutator of the field operator with the momentum operator is I delta of x minus y. So we're treating position like a label, just like these A's labeled the various positions in quantum mechanics. And the Kronecker delta becomes a delta function. And similarly, we should impose that the field operators commute with themselves, as do the momentum operators. And so here, notice I've written the arguments of the fields and momenta as 3 vectors. That's indicating that we're in the Schrodinger picture. So we'll come to the Heisenberg picture later, but all of this is in the Schrodinger picture. Okay. Yes?
Are the computation relations only at equal time?
That's right. Yes, when we go to the Heisenberg picture, we'll see that they'll take commutation relations will take this form at equal time. Here we're in the Schrodinger picture, so the states evolve in time and the operators are time independent. There's no time dependence here. So these are 3 vectors. Okay. So this is the new input. We've promoted our classical fields to quantum fields, and we'll spend the rest of the lecture seeing what the implications of this are. And to do that, we'll need the result from yesterday. We solved the classical Klein-Gordon equation, and what we found is that the solution takes this form. And so this solves the Klein-Gordon equation, which I believe I wrote in components incorrectly yesterday. Thanks to Finn for pointing that out. But this is what it should look like. This solves this equation. And so if we promote field to an operator, we need to promote something on the right-hand side of this equation to an operator as well. And what we're going to do is we're going to promote these coefficients, A and A star, to operators. These functions will become, after quantized, operators, which I'll indicate by subscripts. So A of k will become an annihilation operator, and A star k will become a creation operator, both indexed by a 3 momentum that describes the momentum of the particle that these operators will create or annihilate. And so if we want to work in the Schrodinger picture, we need to pick a time. It's convenient to pick the time t equals 0, in which case we can write the relationship between our Schrodinger picture field operators and our Schrodinger picture creation and annihilation operators. And that will just take the form you can probably guess just by setting t equals to 0 in this equation. So just set t equals to 0 and made this substitution. And so, as you can see, if field operators related to the creation and annihilation operators like this, these commutation relations will imply a set of commutation relations for the creation and annihilation operators. And you'll work out the details of how to go from these commutation relations and this expression to the commutation relations for the creation and annihilation operators in tutorial this afternoon. I'll just give you the results now. What you find is that the commutation relation P is 2 pi cubed 2ek times a three-dimensional delta function k minus p. And the annihilation operators and creation operators all commute among themselves. We also found yesterday an expression for the Hamiltonian, which is a half of pi squared plus a half m squared pi squared plus the gradient term. And if you then just use those relations, you can show that the quantum Hamiltonian can be written in terms of these creation and annihilation operators, like this. And this is, again, a result you'll derive in tutorial this afternoon. And so what does this look like? This looks like, if we ignore this integral, this basically looks like the Hamiltonian for a harmonic oscillator. Just the energy or frequency times this combination of ladder operators. And so we can think about the free Klein-Gordon field as just an infinite set of harmonic oscillators. So again, all these results may seem like I'm pulling out of a hat. You'll derive in tutorial. They just follow from those commutation relations and our results from yesterday. Okay. So now we've written down some of the operators in Klein-Gordon theory. The next thing we want to understand is what are the states in this theory. So the simplest state is the vacuum state, which is a state with no particles. And so if we're interpreting these AKs as annihilation operators, what we mean by the vacuum is the state that is annihilated by all of the annihilation operators for any k. And we can choose a normalization for the state, and a convenient choice of normalization is just to choose it to be unit normalized. So these two properties define what we mean by the vacuum. That's the vacuum state. A natural question to ask is, what is the energy of the vacuum state? So we've only constructed a few different operators so far. Ask, what do we get if we act with the Hamiltonian on the vacuum state? So if we act with the Hamiltonian on the vacuum state, and it turns out to be, it will be an energy eigenstate, what we'll get is that energy, the energy of the vacuum, times the vacuum state. And using our result, the result that you'll derive this afternoon for the Hamiltonian, this is just our Lorentz invariant measure times Ek. This first term has the annihilation operator on the right, so it just gives 0 when we act with it on the vacuum. But this other term survives, so we get a k dagger k acting on 0. And we can compute this by using the commutation relation. So we can swap the order of AK and AK dagger, and we'll just pick up 2 pi times 2 EK times this delta. And that will basically just cancel off the denominator of our Lorentz invariant measure. And what we're left with is the integral of d3k ek times delta 3 of k minus k times 0, which looks horribly divergent. So we've got delta of 0, this integral over all momenta of something that grows with as the magnitude of the free momentum gets large. So this diverges. So why is that? There's 2 different reasons for why this diverges. This is not the only divergence we're going to encounter in this course or quantum field theory courses. Understanding the origin of these divergences can help us understand what's going on. So there's 2 reasons for this. One of which we can think about as coming from the UV or high energy physics, and one of which comes from the IR, the infrared or low energy, long distance physics. And so the IR divergence we can regulate by putting our theory in a box. So by regulate, this is something we're going to do frequently, several times in this course and frequently in QFT2. I just mean modify our theory in some way to remove the divergence, and then at the end we'll undo whatever we did, hopefully after we've, and hopefully we'll be left with a finite answer in the end. Although in this case, we won't. So we can regulate our theory by introducing a box, by putting our theory in a box. Size L. And if we're in a box, we can understand the origin of this delta of 0 as follows. So the delta is, you can think of as the Fourier transform of 1. So we can write this as the limit as L goes to infinity, integral of from minus L over 2 to L over 2, d3x e to the I x dot p. So this would just give us a delta of 2 pi cubed delta of P. So if we set P equals to 0, we recover the 2 pi cubed delta of 0. And, well, this exponential with P equals 0 is just 1. So this is the same as the limit as L goes to infinity of d3x. And this is just the volume of our box. So what we can conclude from this calculation is that the energy of the vacuum diverges because we're considering a theory in Minkowski space. And space is infinite in Minkowski space. So of course, we get that the energy of the vacuum is infinite in an infinite space. The only way that the energy could be finite in an infinite space is if the energy density is 0. So I understand part of the origin of this divergence, and that's because the total energy diverges if V diverges unless rho naught is 0. Okay, so maybe a better question to ask, instead of what is the energy of the vacuum, we can ask what is the energy density of the vacuum. So the energy density of the vacuum is the energy of the vacuum over the volume, which we can, using our expression for the energy up here and the volume, we get this is equal to the integral d3k of over 2 pi cubed a half ek, which still diverges for large. If the free momentum has a large magnitude, ek goes like k. So this is an integral k squared dk times k. It still diverges for a large magnitude of the free momentum. And this is a UV divergence. And UV divergences will be extremely common moving forward. And there's several ways we can understand them. So this is only a real divergence if we trust our theory up to arbitrarily high energy. For most interacting theories, that's a bad assumption. There's reasons that we'll talk about that later, that we expect most of these theories just to be valid for some finite range of energy up to some maximum energy scale, in which case we expect new physics to enter. There's no, in principle, problem with having a free theory up to arbitrarily high energy, but this is a special case. And at this point, if we assume that this is a theory that's valid up to arbitrary high energy, then we really do have a UV divergence, and the energy density is infinite. But it's not so much of a problem. Most of the time, we're only, well, if we're doing non-gravitational physics, the vacuum energy doesn't really affect anything. So one possible exception that we'll also look at in tutorial is the Casimir effect. But even there, what really matters is energy differences in the vacuum energy between different configurations. And possible reason we shouldn't be too concerned about this is that when we went from the classical theory, the quantum theory, there was an ambiguity. Classically, the commutator of phi with pi is 0. So we could add any multiple of that commutator to our classical theory if we like. We wouldn't change the classical theory. We would change the quantum theory. So, and that would change the vacuum energy. So our perspective is we're just going to ignore this problem. It's not a serious problem because it doesn't affect any observations. And that's going to be a common feature of quantum field theory. So we'll often get infinite answers if we're not asking a physical question. If we're asking a physical question about something we can actually measure, then we better get a finite answer. But there are many questions you can ask in quantum field theories that can't in principle be measured, and there you often get infinite answers. And so our perspective is we're just going to remove these infinities by normal ordering, essentially all of our operators. And so we will take our Hamiltonian and normal order it by moving all of the creation operators to the left by hand without using the commutation relations. So if we do that, we get the integral d3k over 2 pi cubed to ek, ak dagger. Okay. So I've just, by hand, in the second term, moved the creation operator to the left of the annihilation operator. And so then if we act with this normal ordered Hamiltonian on the vacuum state, we have an annihilation operator on the right, and the vacuum energy will be 0. And we'll basically only be dealing with normal order operators from here on out. Any questions on that?
So this procedure is supposed to be valid for small energies? Is that the idea?
Okay, so
why would this give the same answer if you just flip the...
This will give a different answer. But the claim is that it won't affect any of the observable physics. This is not something we could actually measure if we're doing non-gravitational physics, which we'll assume throughout this course that we're not dealing with gravity. So without gravity, there's no way we can measure the vacuum energy directly. We can only measure differences in energy. And the differences in energy between any two states will be the same for this normal ordered Hamiltonian and our original Hamiltonian. So we're not changing the observable physics by doing this.
You're changing the order just because you can use the commutation relations, and you don't care about the constant, right? Or is there?
That's right. We just don't care about the constant.
But if they didn't have these commutation relations, you wouldn't just do it willy-nilly.
That's right. So later in the course, we'll normal order things like the momentum operator or angular momentum operator, operators that we deduced their original form from classical physics. So there's an ambiguity in going from classical physics to the quantum physics, and that ambiguity is basically a constant. And if we normal order, we're just setting that constant to 0. And so the constant is usually uninteresting.
Can you just explain again why one is infrared and one is ultraviolet? So it's ultraviolet because it just goes to high energies, and why infrared again?
Right. So this comes from high energies or large momenta. So if we set h bar and c equal to 1, energy and momenta have the same units. So, or alternatively, if we take a particle of fixed mass and send the momentum to infinity, the energy will also go to infinity. That's why I'm calling this a UV divergence. I'm calling this one an IR divergence because it's basically coming from p equals 0, from 0 momentum. Alternatively, we can think about this as coming from long distance physics. So IR either means low energy or long distance. And the volume goes to 0 only if the size of our space goes to infinity. So, the volume goes to infinity only if the size of our space goes to infinity. So this divergence, there should be a limit. So it goes to infinity here. So this is coming from long distance physics. Other questions? Okay. So the next simplest states in our theory are the one particle states. And the one particle states are formed by acting with a single creation operator on the vacuum state. And I'll denote them by k, the 3-vector k. But it's important to note that these states have definite not only free momentum, but also energy. These are states of definite momentum and energy because if they're it's a physical state, these states satisfy k squared equals m squared. So if we know the mass and we know the free momentum, we also know the energy. And so sometimes you'll maybe see in some of the references I suggested, see one particle states labeled by the form momentum. And that means precisely the same thing. So this is a redundant description. We don't need to specify the energy if we know the mass and we know the free momentum. And these states are not unit normalized. So if we compute the overlap of P with K, what we get is 0 AP, AK dagger, which we can compute, again, by using the commutation relations between AP and AP dagger. And we get 2 pi cubed, 2 EK, delta P minus K. And so this is why we went through the trouble yesterday of writing our solution to the Klein-Gordon equation in terms of a Lorentz invariant measure, because now we have a Lorentz invariant normalization for our states. So it's basically the same kind of argument that it tells us this is Lorentz invariant as here. So we've got 2ek instead of 1 over 2ek, and we've got a delta function instead of an integral d3k. And our delta is kind of the opposite of integrating with respect to a variable. But this is Lorentz invariant. Okay, so these are our momentum states, momentum eigenstates. We can also in a looser sense, try to write down states that are localized at some position. So we could try to write down this, and we'll often be interpreting this as a one-particle state localized at x. But I'm not going to write down a position operator to show that. Instead, I'm just going to argue that this should be a one-particle state localized at x based on a few facts. So one is that this is a one-particle state. We can show that by defining a number operator, which is an integral d3k over usual 2 pi cubed 2ek of ak dagger ak. So if we act with this on, say, this one-particle state, we'll get back exactly the same thing. So if we can use the commutation relations to, so n times ap dagger of 0 is ap dagger of 0. So if we commute the ak past the ap dagger, we'll get a 2 pi cubed 2ek delta, which will kill the measure and integral, and we'll just be left with an ap dagger. So this our one-particle states have eigenvalue 1 under this operator. And if we put more creation operators here, we get that would be a multi-particle state, which I'll come to in a minute. We'd get this n just counts the number of particles in the state. And this is a one-particle state in the sense that this state has eigenvalue 1. We act with n on 5x. We just get back 5x acting in the vacuum. And that's because 5x basically has a single annihilation operator, a single creation operator. The annihilation operator annihilates the vacuum. The creation operator will be the same story as here. So this is a one-particle state. That's definitely true. And in what sense is it localized in x? It's localized in x in the sense that if we compute k phi of x 0, we'll get e to the minus I k dot x. This is a computation you'll also do in tutorial. Which is the same as you would get if you computed the overlap of a momentum eigenstate and a position eigenstate in quantum mechanics. So in this sense, we can think about 5x acting on 0 as a one-particle state localized at x. Any questions on this? Okay. We've almost classified the states, but there are also multi-particle states, which we can get just by, we want a multi-particle state with n particles of momentum k1 up to kn. We can get such a state just by acting with n creation operators on the vacuum. And that's a multi-particle state. So one thing we notice is that the AK daggers all commute among themselves. So the particles we're creating are bosons. And these states, with n particles here, will have an eigenvalue of n under that number operator. So, as you can probably guess, based on the form of our number operator and our normal ordered Hamiltonian, these two operators commute. They're basically the same operator, just the number operator doesn't have this extra factor of e. So the extra factor of e doesn't affect whether it commutes. So this is telling us that particle number is conserved. So this theory doesn't do one of the very first things that I said we wanted a quantum field theory to do, is describe processes where particles are created or annihilated and particle number is not conserved. And the reason for this is basically we're just considering too simple of a theory. This theory has no interactions, essentially. And this is a very special property of this theory. And almost any possible change we can make to the Hamiltonian will make the commutator of H with n non-zero. And we will be able to describe particle creation and particle number non-conservation. And so these are all of the states in these states and linear combinations of these states are the only states in this theory. And so our state space is what's known as a Fock space, which is just a direct sum of the n particle Hilbert spaces. So these states I described are the states of definite particle number. We can also create superpositions of states that don't have definite particle number. Everything I've said so far has been in the Schrodinger picture. And as Jessica was asking earlier, it's often useful to go into the Heisenberg picture, where our operators depend on time and our states are time independent. So in general, a Heisenberg picture operator is related to a Schrodinger picture operator by the usual formula. We just multiply by e to the plus or minus IHT on either side. This is the Schrodinger picture. Heisenberg picture operator. And so what we're interested in, computing the time dependence of our creation and annihilation operators and also our field operators. But if we get one, we can find the other. We know the relationship between the two. And so the annihilation operator in the Heisenberg picture is related to the annihilation operator in the Schrodinger picture by this formula. And we can, using the BCH formula, e to the a times b e to the minus a is b plus the commutator of a with b plus half a with ab, and the commutation relationship between h and a. So a just lowers the energy by EP. So not surprising that this is the commutation relation. We get that this is just e to the minus EPT. Maybe. Which is what you would expect. This lowers the energy by EP if we acted with this on a definite energy state. Just to get this extra time factor, time evolution factor. And similarly, we'd get the same thing with the opposite sign and the exponent for the creation operator. And this tells us that the field operator is then integral d3 k So if we just plug these expressions into our expression for the Schrodinger picture field operator, we basically get back the time dependence we started with. And this is the Heisenberg picture field operator, which is precisely what you'd expect. This is just the original solution we had to the Klein-Gordon equation with the functions a of k and a star of k replaced with the annihilation and creation operators. So I've taken the perspective that we started with these commutation relations and our classical solution, and everything else followed. It's not the only possible way we could end up with the results that we've derived. We could also start, we could just take this as the definition of phi and assume that we have creation, commutation relations between the creation and annihilation operators, that those work in the same way, that those create our momentum eigenstates. So if we assume this relation between the two, then we could also determine how phi had to evolve in time, or how these operators had to evolve in time by looking at the Heisenberg equation of motion. And so in other words, we could take this as a definition, and then all of the physics would be in the algebra of the creation and annihilation operators and in the Hamiltonian. And just as a check to see that everything we're doing is consistent, we can compute the time evolution of this field operator in the Heisenberg picture. And we expect just to get minus I times the derivative of phi. That's the Heisenberg equation of motion. And so we can compute this. Our Hamiltonian is just this. Should write. Sorry, I'm not going to have enough space here. Let me write this on a different board. So two momentum integrals. And we're computing the commutator of EK, A dagger K, AK. AP, e to the minus I p dot x plus p dagger Okay, so here's the integrand of the Hamiltonian. This is the integrand of the field operator. And so in this, for this first term, we need to compute. We can commute the AP with the AK dagger. And what we'll get is minus EK, AK, the minus I k dot x. So we'll also get a 2 pi cubed 2 EK delta k minus p, which you can use to do this integral. And then over here we'll get EK k dagger I k dot x. Which is just what we get, computed the time derivative of our field operator. Just bring down a factor of plus or minus dk. So this is all consistent. Any questions at this point? Okay. So just a few comments on interacting field. So we can imagine we've got an interacting field. So we can always write an interacting field in the same way in terms of the creation and annihilation operators. Just suppose that there's some other creation and annihilation operators for the interacting case. And so this is an interacting field. And so we can write an expression like this. And the physics of the interacting field is not going to be in the relationship between the field and its creation and annihilation operators. All the physics will be in the time dependence of the creation and annihilation operators. So at any fixed time, these creation and annihilation operators should work in the same way as the free theory. So expect interacting theories still have states with 0, 1, or multi-particles, and there's some operators that we can use to create or annihilate particles. And so we'll just call those operators BP dagger and BP. So at fixed time, at any fixed time, BP dagger T and BP T work the same as in the satisfy the same algebra as the free theory. And what will change in the interacting theory is this derivation. The Hamiltonian will determine the time evolution. And so these creation and annihilation operators that, they create the annihilation operators, or the creation operators that create a momentum state P will mix as time evolves. So that's that will be the difference between the interacting theory and the free theory. The difference will not be in the relationship between the field operators and the ladder operators, but rather in the time evolution of the ladder operators. So we'll come back to interacting theories tomorrow. Okay, so we're dealing with a free theory here, which means there are no interactions. Remember, one of our main goals for this course is to calculate decay rates or cross sections. They're not interesting in a theory with no interactions. So we won't try to calculate those for these theories. This is a theory where particle numbers conserved and no interaction, so trivial to compute what's going to happen in a scattering experiment. Our final state will just be the same as our initial state. But there are still some interesting questions we can ask about this theory. And one is, what is the amplitude for a particle to propagate 2x from y? So remember, we're thinking about this as a one particle state. At y. And because our fields are real, this is a one particle state at x. Okay. And so let's compute this and see how to interpret it. So for each of the field operators, we get Lorentz invariant measure. And then there are 4 terms. If we expand out each of the field operators in terms of the creation annihilation operators, we've got the AP. We have an AP, so if we say this one contains the P's, this has an AP dagger and an AP term. The AP dagger term will give us 0. So if we act from the right on the bra vacuum with the creation operator, we get 0. And this one will contain, again, 2 terms, but only one of them is non-zero, and that's the one with the creation operator. So we'll get an AK dagger 0. And the other 3 terms vanish in the 2 times 2 terms we would have. And so we just get, this is the only term that survives. And this is calculation we've essentially done many times. This lecture, we can just use the commutation relations, killing one of the measures and setting p equal to k. And so what we get then is this. And so we have e in the exponent e to the I, e dot x minus y. K just becomes p from the delta function you get from the commutator. Okay? So this is the amplitude for a particle to propagate from y to x. Let's look at what this propagator looks like if x and y are space-like separated. So if x and y are space-like separated, then we can choose a frame where these two events happen at the same time, and their distance r away. And in that case, we get this integral. Certainly doesn't look like it's going to be 0, which is a little bit strange. So if this is not 0, then we're saying that there's a non-zero amplitude for a particle to propagate outside of its light cone. And it turns out this is not 0. This can be evaluated exactly in terms of special functions, and what you get is a modified Bessel function of the second type, which asymptotically looks like m to the 3/2 over 4 pi squared r to the 3/2 pi over 2 e to the minus mr, as r goes to infinity, which is not 0. And that probably should be surprising to you. We have just calculated the amplitude for a particle to propagate from y to x, non-zero even outside of the light cone. It goes to 0 rather quickly. As we get farther and farther outside of the light cone, it goes exponentially quickly to 0, but it's not 0 anywhere outside of the light cone. So, well, this is only really a problem if it violates causality. So if we can use this to send information, or we can influence events outside the light cone. If it's just a correlation outside the light cone, that's okay. So what we really care about, if we want to preserve causality, is that a measurement at space-like measurements can affect events at space-like separated points. And so that will be true as long as, so if the commutator of phi of x by phi of y is 0, which I'll call delta of x and y, or delta of x minus y. It's only dependent on the difference. This will ensure then a measurement at x cannot affect and vice versa. So I want to check that causality is observed. We need to compute this commutator, which is equal to d of x minus y minus d of y minus x. Note I have not put any vacuum states on, not sandwich this between the vacuum states. It turns out that this is also equal to the vacuum expectation value of this commutator. And so in our calculation over here, in this step, we ignored 3 terms because they annihilated the vacuum. If we compute this commutator, those terms we ignored will instead cancel among themselves. So for instance, we would have an AP term, AP-AK term in this one, and an AP-AK term in this one. They'd have the opposite signs and cancel. Yes?
How did you get that first equality? The commutator is equal to d minus d.
This one?
Yeah. Like,
Okay.
don't those d's already have a vacuum sandwiched to them?
So here, this is just, this d just is the product. So this equality, going from here to here, we can just write out the commutator. We've got this is equal to 0, 5x, 5y, 0, which is d of x minus y, minus the other one. The claim is that this is equal to this.
That's what you're trying to prove?
Yes. So, for instance, I wasn't going to show that, but I can. If the reason is that, so in going from here to here, we threw away terms like AP, AK, because now it's a vacuum. So we would also get a term like another term from the opposite combination. We'd get this term from d of x minus y. We'd get exactly the same term, just with opposite signs here, for d of y minus x. And then we could just flip the signs in the exponents by taking k to minus k. One of the integrals, cancel them out.
I still understand. On the left side, you have the operator.
Yes. So the commutator of 2 operators can be an operator. It can also be a number. So for instance, some of the first commutation relations I wrote down, we had that the commutator of, or it can be a distribution, the commutator of phi with pi was I times delta. Was there another question? Yes?
Why is it if the commutator is 0 that the measurements can't affect each other?
Well, okay, so so let's look at what's going on here. So what's going on? is that if we've got field at, we measure that there's a particle at x and there's a particle at y. We can't tell. So there's a non-zero particle for the particle to propagate from x to y. There's also a non-zero particle amplitude for the particle to propagate from x to y. And if we just measure that there's a particle in x and y, we can't tell which happens. And these two amplitudes cancel. So if we compute this commutator, this is 0. Okay. So yeah, the claim is that this commutator is 0, and we can see that just by writing out a result. So we have that this is our result for and if we take p to minus p in one term, measure doesn't change. We just flip the sign here, and we get e to the I PR minus e to the I PR, so we get 0. Commutator does vanish. This is saying that the amplitude propagate from x to y is same as the amplitude to propagate from y to x. If we were dealing with a field whose particles who had distinct particles and antiparticles, then this cancellation would be between the amplitude for a particle to propagate from x to y and an antiparticle to propagate backwards.
What's like the justification for why we can take p to negative p or k to negative k kind of info? Like...
Okay, so if we look at this measure, so first of all, EP is even, so that doesn't change. What happens if we take let's look at just a one-dimensional example for simplicity. So if we're looking at the integral dp from minus infinity to infinity, and we take p to minus p, this becomes the integral from infinity to minus infinity of minus dp. And then we can swap the limits of integration to get the integral from minus infinity to infinity dp, where this is our new one. Oh, this is our new variable. And we can just do that for each of the 3 directions of space. Yes?
Yeah, so you're saying that the particle propagation probabilities from x to y and y to x cancel each other, and so we can't detect the difference.
That's right.
Does this happen just because this theory is sort of free and has some kind of symmetry over space, or does it happen generally?
It happens generally. So it would be a problem if these amplitudes didn't cancel. Then physics outside of the light cone would be affected by what's going on at some point x. So this will cancel more generally. Although it's a special case of the free theory is that this vacuum expectation value is equal to just the commutator. In general, this commutator will be an operator.
Could you just say that because they're space-like separated, you could Lorentz transform so that it happens like at equal times, and then at equal times you know that the commutators that it commutes. Like if you didn't use the fact that that x naught and y naught
Yes, that's another way we could do that. Yes.
But wouldn't this relation also mean that the correlation inside the light cone is also zero?
No. So it would if you're assuming it's an analytic function. It's not an analytic function. So this is telling us that, well, either we've got a completely trivial theory, or there's something non-analytic going on, and it's the latter.
When you say amplitude, you mean like the amplitude change? You mean like the change in the probability of
By the amplitude, I mean precisely this. So here we've got, I'm thinking about this as like our initial state, and this is our final state. So we've got some amplitude propagate from here to here. This is just in general. This is a quantum mechanical amplitude.
So what exactly is it describing physically?
So my interpretation of this is we're thinking about this as our initial state. So this is a single particle at y, and then our final state is a single particle at x. Yes.
There on the multi-particle states, we wrote that if you act multiple times with the creation operator, then you're getting lots of different particles, right?
Right.
So knowing nothing about this, I would have thought that you'd get a single particle that's excited multiple times. But
Okay.
so where exactly does that come from, that first line?
The first line? Well, so we'll go. Some of the statements I'm about to make will show in tutorial, but what you can show is that acting with the creation operator, I've referred to this a few times, raises the energy by EK. It increases the momentum by K. That's exactly what you'd expect if you added a new particle of energy EK and momentum K. Whereas if you just excited, and in particular, our formula for the energy involves the mass. So if you were just had a single particle that you were exciting more, you wouldn't expect that have these relationships between when you acted with the new creation operator to increase the energy by EK and the momentum by EK. That's another. It has a very natural interpretation of just adding a new particle with that energy and momentum.
And is there some way that we can get antisymmetric wave function out?
Yes, we can. If we started with anti-commutation relations. And that's precisely what Tibber will show you how to do.
When we define the propagator over there, we have it sandwiched between the states, right? But when we do the commutator here, we don't have the original.
That's right. So the claim is that the extra terms, like this one, that would vanish if we sandwich them, cancel between d of x minus y and d of y minus x. They cancel. If you just write them out, all you have to do is do this change of variables, e to minus p. So probably not going to have time to finish everything in the lecture notes, but just want to look at the propagator delta outside of the light cone and show that it's non-zero, or inside of the light cone. So for time-like separations, we can compute this. And what we get. So I'm going to do some manipulations that will look a little bit strange, but might be easier to understand going backwards. So the first thing I'm going to do is write this as 1 over 2 EP e to the minus I p dot x minus y e naught equals EP. That's the first term. Pull this out. I haven't done anything interesting here. We've always implicitly had the 0th component of P be equal to EP, so nothing's happened here. For the other term, I can write this as 1 over minus 2 EP e to the minus I dot P x minus y, evaluated at P naught equals minus EP. So what have I done here? So what I've done here is I pulled the minus sign out. Okay, nothing interesting there. This term, we're evaluating P naught with P naught should be equal to EP. Here I'm evaluating it with P naught equal to minus EP, so I flip the sign. That also flips the sign of the spatial terms. But as we've seen several times, the signs of the spatial terms doesn't matter. We can just change those by taking the 3 vector P to minus the 3 vector P. And for x naught greater than y naught, I can write this as a contour integral. And so here, this contour, which I'm calling CR, it's a contour in the complex P naught plane. Which goes around the poles at EP, P naught equals plus or minus EP in the following way. So it just goes above them. So these two expressions are the same. So if we do this contour integral for x naught greater than y naught, we can close the contour integral in the lower P naught plane. And we'll just pick up the contributions from the residues of the two poles. And so those are these two terms here. On the other hand, if x naught is less than y naught, then we need to close the contour in the other direction, and there'll be no poles, and we'll get 0. So this expression is equal to this expression if x naught is greater than y naught. So we can write this as I'm putting in a Heaviside function. And so our expression for this in more compact notation is the integral over d4p I over p squared minus m squared e to the minus I p dot x minus y. Just done some odd-looking manipulations. I'm out of time, but we'll come back to this tomorrow and see why this is useful. So where we're going tomorrow is we'll finish up discussing these propagators, and a closely related object to this retarded propagator we've just discussed, known as the Feynman propagator, will be one of the building blocks of perturbation theory. So we'll derive that result. That'll be our most important result from the discussion of the free flying Gordon theory, and then we'll turn to cross sections and scattering amplitudes. So we'll come back to this tomorrow. Any questions? Yes.
Why is that when x0 bigger than y0, we have to close the contour on one side, and in the other case we have to close the contour?
There should be an I here. It's because we want to make the new part
to go
exponentially to 0.
Thank you.
Any other questions? Okay, I'll see you this afternoon.